2 billion kilometers deployed around the world, optical fiber is the backbone of today's most advanced telecommunications networks. Fiber is assembled into optical cables that link continents, cities, and neighborhoods around the world. This thin, flexible strand of ultra-pure glass is capable of carrying voice, data, and video information in the form of light signals at very high speeds. Let's take a closer look at this revolutionary transmission medium. Optical fiber is very thin. One strand is about the diameter of a human hair. It is comprised of two basic elements made of glass, the core and the cladding. The core, the center part of the fiber, is the area through which the light signals are transmitted. The cladding layer completely surrounds the core, keeping the light from escaping. There are two different types of fiber, single-mode and multi-mode. Single-mode fiber has a small core diameter designed to carry light in a single path over long distances. It has high information carrying capacity and low attenuation, and is the most widely deployed optical fiber in the world. Multi-mode fiber has a larger core, which allows light to travel down many paths simultaneously. Typically, multi-mode fiber is deployed in data centers, local area networks, and storage area networks, where it is more cost-effective than single. Attenuation refers to signal loss along the length of the fiber. In this illustration, the light gets dimmer as it travels down the fiber. It can be caused by the quality of the glass itself, or can be induced by bending. Dispersion is the distortion of a signal along the fiber length. This occurs because different spectral components of the optical signal in the optical fiber travel at different speeds. In this example, different wavelengths are represented by the red and yellow light. Macrobending and microbending are optical effects that occur when the fiber is bent from a straight axis. Microbending is an attenuation increase caused by high-frequency, small-radius bends along the length of the fiber. Macrobending is the attenuation associated with bending or wrapping the fiber. Both of these conditions can allow light to leak out of the fiber, meaning some of the original signal is lost. Using a bend-insensitive fiber like Corning ClearCurve single-mode or multi-mode fiber will greatly reduce the loss caused by macrobending. Optical fibers operate on the principle of total internal reflection, which keeps the light within the core and guides it down the length of the fiber. Refraction refers to the bending of light as it passes from one substance to another. The glass used in the fiber's core has a higher refractive index than the glass used in the cladding, so that the light can be trapped in the core by reflection at the cladding interface, as it propagates down the length of the fiber. Two additional characteristics of single-mode fiber that are important are cutoff wavelength and mode field diameter. Cutoff wavelength is the wavelength above which a fiber will support only a single mode. Wavelengths below the cutoff support two or more modes. The cutoff wavelength is determined by the fiber's refractive index profile, the length and bend of the fiber, as well as the cabling process and deployment conditions encountered during use. In a single-mode fiber, some of the optical power is actually guided outside the core. In fact, as much as 30% of the light propagates in the cladding layer of some fibers. The mode field diameter defines the size of the optical power distribution in the fiber. Multi-mode fiber has two important characteristics, numerical aperture and core size. Numerical aperture is the measure of the angular range of acceptance of light into a fiber. The angle over which a fiber accepts light depends on the refractive indices of the core and cladding glass. Core diameter is a fundamental design parameter of multi-mode optical fiber. The larger the core, the more modes of light can.
Lines are thin, flexible, transparent strands of optically pure silica glass or plastic used to transport digital data via a light source. These strands are typically smaller in diameter than
cable construction. Tight buffered fiber optic cables offer a clear advantage over traditional loose tube constructions by providing excellent fiber protection, easy handling, and fast terminations necessary for high-performance applications. Tight buffered construction starts with our UltraFox or UltraFox Plus fiber. Each fiber is coated with a UV-cured acrylate material to a diameter of 245 microns or 500 microns for UltraFox Plus. The individual fiber is then coated with a secondary buffer to 900 microns. This provides the best environmental and mechanical protection and can easily be stripped directly to the glass for termination with connectors or for splicing. In addition to this overall tight-bound process, OCC has designed additional features into our cables that make it ideal for harsh environments. All OCC cables are helically stranded, meaning the internal elements are twisted together to form a helix. This time-tested cable construction method provides flexibility, survival in different pulls, and mechanical protection for the optical fibers. Helically stranding ensures that no one particular element of the cable receives more stress than the other elements, thus equalizing the stress load associated with particularly tough installations. To add even more protection and durability to our fiber optic cables, we incorporate Aramid strength members to our cable components. With our distribution cable products, the helically stranded fibers are overlaid with Aramid yarn to form the cable core. A pressure extruded outer jacket is then applied to the cable core. For breakout cable products, each fiber is surrounded by a layer of Aramid yarn and then jacketed. The jacketed subcables are then helically stranded together to form the cable core. Once again, a pressure extruded outer jacket is applied to the cable core. All this provides excellent mechanical and environmental protection, allowing cables to withstand the rigors of difficult cable pulls, high tensile loading, and severe crush occurrences. As one more level of OCC's superior fiber optic cable design, some of OCC's fiber optic cables feature a core-locked outer jacket. This unique outer jacket is extruded under high pressure directly over the cable's core, resulting in the internal surface of the cable jacket having helical cusped ridges that interlock with the subcables. This helps keep the cable cross-section circular for better crush and impact protection and superior tear resistance during installation. All of these factors make OCC's cables a practical and reliable means of high-capacity data transmission in challenging environments. Companies that choose
Reel. The color-coded fiber is now ready to be put into loose tube or made into ribbon fiber. For tight buffer cable products, a colored PVC coating is applied that increases the diameter of the fiber from 250 microns to 900 microns. This process is called tight buffering, which, in addition to providing a color to identify each fiber, allows the resulting cable to be flexible, yet rugged and easily mated to mechanical connectors. For these reasons, the tight buffered cable design is superior. Essex utilizes medium-density polyethylene due to its durability, moisture resistance, and low coefficient of friction. High or low-density polyethylene can also be used for select OSP cable designs that require different performance characteristics. Polyvinyl chloride, or PVC, is typically used for the jacket material in our premises cable designs. PVC is a thermoplastic with good flame and abrasion resistance, making it suitable for raceways, indoor-outdoor cable structures, ducted environments, and most riser-rated.
and below the street via large underground copper wires. It passes through small regional networks before ending up here at Telehouse North in London. Telehouse North is England's main internet hub. The IP address on this packet tells the hub that the World Science Festival server is actually in Los Angeles. So Telehouse North sends the packet out as light across the Atlantic, over fiber optic cables buried deep beneath the ocean. The packet ends up here, 60 Hudson Street, New York City, the largest internet hub on the East Coast. This hub sends the packet through a series of regional networks connecting New York to Los Angeles, where the World Science Festival server resides. The packets are sent to LA's One Wilshire hub, which checks the traffic report before sending them off. Through miles and miles of land they travel, checking in through different hubs. Like our New York City tourists, those packets don't care how they get there, as long as they get there as fast as possible. Most of them will go through 60 Hudson in New York, where they are redirected back to England as light, riding a fiber of glass as thick as a silver dollar. Then back on copper wire, through regional British networks, until all the packets reach their destination.
Installed around the world, with the ability to transmit large quantities of information at extraordinary speeds. Fiber optics is the future of communications, rapidly replacing traditional copper wires as the preferred standard for an array